Welcome to this exercises of mathematical proof. So from the definition of integers, we know n is even if n is basically equal to 2k, and n is odd if 2k plus 1. Now it's very important to keep this in mind when we start to work on direct proofs, because in direct proof we start by the assumption that p is a true, and we end up with a q and proving that p implies a q is a true. But in contraposition, we take the opposite. We take the negation of a q and we end up with a negation of p. So we always start by the false assumption of the true statement p, and we want to disprove that so we can have a contraposition. Now finally we have the contradiction. In this case we assume p is false, and we will try to start by a false statement and reach a true assumption or a true q. And in this case we say we can't have not p and p exist at the same time, and this is basically implies if we try to prove that a number is even and odd at the same time. Now let us start by taking the first example, and we want now to prove if the sum of two even integers is even. So what we have two numbers, we have n and m, and both are even. So this is our proposition, and we will start by p to imply that the addition of those two numbers equals to basically an even number, and this is our q. Now we want to start from p, and we end up with a q in direct proof. So basically n equals to 2k, m equal 2k, and now we want to take the addition of those two numbers. So we will take 2k plus 2k, which equals to 4k. Now 4k could be rewritten as 2 multiplied by 2k, and this is basically similar to the definition of integers or even integers. So we can conclude that those two numbers, the sum of those two numbers is even. Now we want to take another example, and we want to prove that 3n plus 2 is even. This leads us to have an n as an even number as well. Now our proposition that 3n plus 2 is even, our q n is even, so we want to start from 3n plus 2, and we will try to prove that we end up with n equal to an even number. So we will know from the definition that basically n equal 2k, and now we want to go from p to prove that we have a q. So we will take the n value, we substitute it in the equation. So this is 3 multiplied by 2k plus 2, which equals to 6k plus 2, and this 6k plus 2 could be rewritten in different format, where we take the 2 out of the parentheses, and this is the 3k plus 1 multiplied by 2. If you give any value or any variable to this equation, 3k plus 1, let's say n, you will have 2n. So we will start from 3n plus 2, and we end up with 2n. So we prove the first ask of the question. Now we want to use the same proof, but in contraposition. In this case we will have the negation of a q, and we want to imply that with the negation of p. So we start by saying n is odd in this case, so it's not p, leads us to not a q. So we'll have n equal to k plus 1, put the value of n, 2k plus 1 plus 2, and this is basically equals to 6k plus 3 plus 2, which equals to 6k plus 5. Now this could be rewritten by taking the 2 out, 3k plus 2 plus 1. And if you call this n, you will end up with the equation 2n plus 1, and this is basically an odd number based on the definition that we took in the previous slides. Now we want to use contradiction to prove the same. So we have 3n plus 2 is even, we have n is even. Now we will start with the negotiation of p, so we have not p, and in this case we will take n as odd, and we will see if we can reach from n as odd, we can reach 3n plus 2 to be an even number. So we take n as odd, in this case n equal to k plus 1 plus 2, which equals 6k plus 3 plus 2 plus 2, and this is basically equals to 6k plus 5. Take the 2 out and you will end up with a 3k plus 2 plus 1, which is basically an odd. We were expecting to reach an even, but unfortunately we reach an odd, so we cannot have p and not p at the same time. So this is contradiction, and n should be an even based on this proof. Now let us take another example. So in this example we have the proposition that if n is even, then n to the power 3 plus 5 is also an odd number. So we have n to the power 3 plus 5 is an odd if n is even. So I will start now by giving p to the fact or to the statement that n is even, and the q stand for n to the power 3 plus 5 is an odd. So I will have n equal to k. I substitute the value of n in the equation, and this is going to be 2k to the power 3 plus 5, which equals to 6k to the power 3 plus 5. Now take 2 out of side the equation, and this is going to be 2 multiplied by 3k to the power 3 plus 2, and give that equation n. So this is 2n, which is basically an odd number. Now we want to do the same, and we want to prove contraposition. Now the contraposition in this case, we want to go from not q then not p, so we want to start by saying that we have n in this case is going to be odd, because we will take the negation of that p. In this case n equal to k plus 1. Now put 2k plus 1 in the original equation. This is going to be 2k plus 1 to the power 3 plus 5. So this is equal to 2 multiplied by 4k to the power 3 plus 6k plus 3k plus 3. Now this is not showing the whole equation, so you can see the title below in the screen to see the full equation, which all equal to n, and this is basically this whole equation refer to n, and so it's 2n, so we end up with an even number, and we prove the equation because we start by the contraposition. We start by odd and we end up with even, so we must, the opposite of that, we have an even and we end up with odd. Now we want to do the same equation by contradiction, and in this case, instead of having n to the power 3 plus 5 is odd, we will assume that we have n is odd and we want to end up with even number. So we will now make the value n equal to k plus 1, and we substitute the value of n in the equation. So this is going to be 2k plus 1 to the power 3 plus 5, and this is basically equal to the same value in the previous slide. which equal to 2 multiplied by 4k to the power 3, 6k to the power 2, plus 3k plus 3. And you can basically say now this is going to be 2 times a value, and this value going to be n, and we start by saying n is an odd, and we end up with having n to the power 3 plus 5 as an even, which is a contradiction, and this is basically proof this equation. So finally guys, I advise you to do this exercise and refer to the definition of real number in the supplement material in the book or in the slides, and try to prove this equation where we have x as a real number. Thank you for seeing this video, and see you in the next one.